you, Evelyn. And thanks for the opportunity to explain my work. Uh, I'm a member of the Computational Biology and Bioinformatics group. This is a biocom group in the Department of Mathematics and Computer Science at the University of the Balearic Islands. And today I will talk about the tool VPF-Class, what is a tool designed to taxonomic assignment and host prediction of uncultivated viruses based on viroprotein families. Okay, what is the goal? The goal is if one user given us a set of viral sequences, then to classify them for taxonomy and for host prediction. And it's important to remark here that this classification is for every viral sequence, and the output is not a clustering of these sequences. And then every classification it's at every level. For example, for taxonomy, we consider 3 different levels of classification for Baltimore, for family, and for genus classification, and it's different each one. What is the starting point of this work? This is from a collaboration with the Joint Genome Institute, and from a paper from the VPES. He provides me 25,000 hidden Markov model, what is a viral protein families, was used to bait viruses. We also use 8,000 isolate sequences as the truth of the classifications from INGVR and Virozone, and also more than 700,000 uncultivated viral genomes. Then our goal is now the first 3 steps to obtain a classification for these viral protein families, and then use it to create the tool VPF-Class to assign a classification for the given sequences. In the first step, to classify and categorize the VPFs, we are using the isolate genomes. In the second step, we are using the uncultivated genomes to provide a better classification from the VPS that are not classified in the step 1. And finally, we validate and reclassify the VPFs using in the previous step. Then in the initial VPF classification, this is the step 1, we compare isolate sequences against viral protein families. We're using HMM scan to infer both taxonomy classification and host prediction. Using this, we are considering all these hits from between proteins and VPFs. And if all these hits are within the same classification, we consider that this VPF is homogeneous for this classification, or it is heterogeneous in the case that we have or we obtain different classifications. In that case, we exclude these viral protein families about our set, or there are no hits between the proteins coming from isolate viruses and VPFs, and the VPF remain uncategorized. Here there is a summary of the different number of VPFs classification at different levels, 3 levels for taxonomy classification and 3 levels for the host prediction. And now the following steps are try to obtain a better classification for the categorized VPFs, or to obtain a classification for the uncategorized VPFs. We consider for the homogeneous VPFs, we are seeing a category. This is category 1 VPFs, and in that group, we consider different quartiles for the taxonomy or thirtiles for the host prediction to rank the set of VPFs in category 1.1, 1.2, 1.3, or 1.4. the best VPF classification will be the 1.1. Then, if we consider these different quartiles or different tertiles, we obtain a classification for the VPFs in category 1.1, 1.2, 1.3, or 1.4. For instance, if we have a specific VPF with, for instance, 7 hits from proteins designed to VPFs classified in the same classification, then we consider a category 1.2 for this VPF. Now the second step is try to obtain or compare the uncultivated sequences using against viral protein families. And then for each classification level, we infer the class of each uncultivated viruses from its hits against homogeneous VPFs. This is, we can obtain an heterogeneous classification for every uncultivated virus genome. Now the idea is to associate for every uncultivated viral genus V 2 scores. The first is the virus hit score, which are computed for the normalized score coming from the HMM search of all hits and the categories assigned to the matched VPFs in step 1. And also considering the percentile rank of its virus hit score in the distribution of all of these virus hit scores obtained for all sequences, we consider a confidence score. And then for every classification for this virus, we consider the membership ratio, that is a percentage of this classification for the virus. This is an example of how it works. For example, if we consider an uncultivated virus with 3 genes with hits to category 1 viral protein families, that is the homogeneous one, classified in step 1. And for instance, if we consider a first hit with normalized sequence score of 300 for the VPF classified as myoviridae in the category 1.1, another hit in the same classification with a viral protein family of category 1.2, and finally another hit in the classification of Cyphoviridae. This is exclusive for the family level in the taxonomy. Then we compute, here appears the formula, and we obtain a virus hit score of this computation. And then the classification assigned to this uncultivated virus genome is an 100% of myoviridae and 12% of Cyphoviridae. And if we consider this virus hit score for all the others uncultivated viral genomes considered in this step, we obtain a confidence score of 0.36. And then the final step in this first part is the cross-validation and the reclassification of viral protein families. This is to repeat the step 1, adding the information and the prediction obtaining in the previous step, only for the UVIGs with a confidence score enough good, that is more than 0.5. At this point, we can obtain that some viral protein family categorized at category 1 in the first step now comes to category 1 or category -1, could be heterogeneous now. Or some unclassified viral protein families now could be also unclassified, that is category 0, or could be categorized all of its hits under the same classification, that is category 1, or could be heterogeneous. By this way, we can obtain more number of viral protein families classification. Then, for example, for the family taxonomy level, a reclassified viral protein family looks like a percentage in every classification and then category for every one of these classifications. As a result, we can obtain 24,000 VPFs classified at Baltimore level, 22,000 classified at family level, and 19 at genus level. Most of them are classified at double standard DNA. We can obtain 40 different representative families, and most of them are from the order of Caldovirales, and more than 200 different genus. These are the most common in the results. And for the host prediction, the diversity of the viral protein families obtained are 23,000 for the domain level, 19 for the family level, and 90,000 for the genus level. Most of them are classified as bacteria at the domain level, and we have 58 different representative families and 67 different represented genera. Now, once the classification of a group of viral protein families has performed, we consider the tool VPF-Class. What is implemented in our tool? First, when the user input the viral sequences in our tool, we consider to find the proteins of each sequence using Prodigal. All these sequences are matched against our set of VPFs using HMN search, and the result of this tool, the output, is to obtain a heterogeneous classification with a membership ratio of this classification for every sequence from the VPS classification obtained in step 3. What are the inputs? Are the VPF models, which are provided by us, and the VPF classification. This is the result from step 3, and the score samples from the uncultivated viral genomes. What is the different confidence score, which also provided by us, and obviously the user viral sequences. And then what is the output? The output of our tool is one table per classification level with the following columns. In that case, we obtain 6 tables, one for every taxonomic or host prediction rank level. And at every level, you can find the virus name, what is the name given from the input FASTA file, the classification name at this level, for example, Syphoviridae classification, a membership ratio of this classification, a virus hit score, which I explained it, that it's an aggregate HMM score from the protein hits, and the confidence score, which is a percentile rank of this virus hit score in the distribution of all analyzed uncultivated viral genomes. Then each row in this classification is a possible classification of a sequence. How these results can be interpreted? If we group the output table by the virus name, one gets a distributional classification with weight, that is the membership ratio, a virus hit score, and the confidence score, which is a reinterpretation of how good is my result for a number between 0 and 1. And at this point, I would like to share you a demo about how it's possible to use the VPF-Class. At first, the tool VPF-Class has implemented using Haskell. Then it's necessary to install a stack to compile the project. The required data, we are the VPF model, the VPF classification, and the scores. which must be put in the same file. And for instance, if the input sequence are a metavirome, in that case from an hypersaline environment, now the options which the program requires are the data index, that is the file with the required data, the input sequences, that is the sequence for the, in this case, for the hypersaline environment, and the tool output, in that case, in that path, the output of the tool. I will move to the most important thing now. I think that this is how one can obtain the classification of the use of the tool. This is the output. These are the 6 different files. And for instance, if we focus on the output for the genus level of taxonomy, we obtain a table like this one, that is for every sequence we have a classified at the genus level, in that case, with a membership ratio, with a virus hit score that is designed for the sequence, and the confidence score for that sequence. In that case, if we analyze what is the confidence score of all the input sequences, we can show that in that case are good enough, and must be present that we can offer a high number of classifications for every sequence. That is, for instance, this is the median of the classifications assigned for every sequence. But most of them will be spurious. That is, that the membership ratio is very low, or the confidence score is also very low. Then we can filter it by, for instance, a membership ratio more than 0.25 and the confidence of 0.35. And in that case, the tool provides you a single classification for every sequence.
You have 2 minutes left.
Okay. Finally, if we filter using these considerations here, this one, then you can obtain, for instance, a single classification for a sequence with a confidence score, and you can perform, for instance, what is the best membership ratio for everyone, and you can offer, for instance, which number of viruses are classified in the same genus. In that case, that is the most represented genus in the input set, and offer like pictures like this one. Thank you very much. And finally, yes, this is a work that is a collaboration between some people from my university and others from the JGI. Thank you, and I will enjoy to answer your questions. Thank you.
Thanks a lot, Juan. I'm going to ask you one question now, and the rest you can either come back to it on the chat, or we will discuss them in the panel. Okay. A quick question: does VPF-Class have a minimum length requirement for input?
No. There are no minimal length requirement. No.
And are there maybe lengths that you would say, oh, don't do 200 bases, or is there a kind of a minimum good length intuitively?
It's based on the hits. If you cannot provide, if you cannot obtain any protein using prodigal from this sequence cannot be classified, of course.
Okay, so then you need to be really lucky if you have very small fragments. Okay, and thank you very much for presenting VPF class, and we'll see you again in a little bit.